All right. So this is chapter 8.2 CFU with two concepts, actually. Concept 1 on conditions for estimating proportion P, and concept 2, constructing a confidence interval for population proportion, right? So concept 1, conditions for estimating population proportion. Concept 2, constructing a confidence interval for a population proportion. So students should be able to state and check the random 10% rule and large counts conditions for constructing a confidence interval for population proportion. Students should be able to construct and interpret a confidence interval for population proportion. So let's dive in. Right, according to a recent study, not everyone can roll their tongue. It's hard to roll the tongue. All right, a researcher observed a random sample of 300 adults and found 68 who could roll their tongue. So use the 4-step process to construct and interpret a 90% confidence interval for the true proportion of adults who can roll their tongue. So, ladies and gentlemen, so this is, we don't have any information about the parameters, right, from the population, but we are using a sample of 300 adults, and we're using that to actually help us estimate what the true population proportion is. So state. So you need to say, we wish to construct a 90% confidence interval. Okay, what's the, in context, what we're trying to find, construct a 90% confidence interval for the true proportion of adults who can roll their tongues. Okay, so that's a statement that we need to put in state. For plan, usually in plan we are looking at the conditions, right? Whether the conditions conducive to do a confidence interval. So one of the very first condition is that we need a random sample. And you should be able to go to the question and then find, where is it? Where is this statement? Right here, right? Random sample. Okay, second thing is because this is a proportion problem, right? We're dealing with proportion, we're dealing with categorical data, whether can they or can they not roll their tongue. We have to use to check for normality, right? N times P. So N times P equals to 300 times 68 over 300. So because the proportion, we don't know the population proportion, we do know the sample proportion. So it's N times P hat equals to 300 times 68 over 300 equals to 68. And that is more than 10. Woohoo! Okay, next condition, we have to do N times 1 minus P hat equals to 300 times 1 minus 68 over 300. And that gives us 232. Woohoo! Class, notice something. If you add 232 and 68, that actually gives you 300. So we sometimes look at 68 as success, and then we look at 232 as failures, right? Success and failure. So 68 of the 300 was successful. 232 of the 300 was not successful. Okay, so the third condition is the 10% rule, which means the sample size needs to be less than 10% of the population size. So now in the question, no population size was given. So we don't know, we are only given the sample size. Sample size is 300. So can you make a reasonable assumption? Can you safely assume that there are more than 3,000? How did I get 3,000? If you take 300 and you multiply that by 10, right, the 10% rule, if you multiply that by 10, is it reasonable to assume that there are more than 3,000 adults in the population? Yeah, I think so, right? Okay, so to continue the 4-step process, the third step is to conclude. So we know that we needed to find the 90% confidence interval. And by the way, confidence interval, a lot of times we abbreviate it to be C.I, so CI, confidence interval. And the formula for confidence interval for proportion is actually P hat plus minus ME. ME, you need to understand that ME represents margin of error. Now, margin of error also has a formula. It goes like this. So Z star times the square root of this entire thing is underneath the square root, right? It's inside the square root. It's P hat times 1 minus P hat divided by N. Now you need to understand also, or remember that P hat is actually sample proportion, right? So we need to calculate sample proportion. Now in the question it says 68 of the sample. Anyway, the sample size is 300. So 68 out of 300 is the sample proportion. And it's easier sometimes to work with decimals, and we convert that to 0.227. Now, if you look at the formula, everything we have the P hat, we have the N, which is 300. The only thing we do not have is the Z star. Now, let me explain first of all, to find Z star, you need to do Z star equals to inverse norm or 0.95, right? Put that in a calculator, and that equals to 1.645. By the way, to find invert norm, we usually go to second verse. Now, to understand a little bit more about what Z star is, now we draw a normal distribution, normal curve, normal density curve. Now, 90% confidence interval is the middle 90%, right? Middle 90%. So the side would be 5%. Okay, psi will be 5%. So in order to use inverse norm, we want to find the Z star on the right and negative Z star on the left. We only need one. We only need to find the positive Z star. So on the calculator inverse norm, they usually use the area to the left. So we need to calculate this orange part. So this middle part, which is 0.9, plus the corner, the tail, which is 0.05, give us 0.95. So you always need to remember to add the area to the left, right? Inverse norm to find the Z star is usually we need to calculate all the areas to the left. So in this case it's 0.95 and it's 1.645, round to the 3 decimal places. So to continue, we know what P hat is, 0.227 plus minus Z star is 1.645, and then we put all the values in, P hat, and we put N in. Then you need to do it step by step. If you're doing by hand, you need to work out step by step. So I prefer to do everything underneath the square root sign first. So 0.227 plus minus 1.645, and everything in the square root works out to be 0.0242. And then we multiply 0.0242 by the Z star, which is 1.65, and that gives us 0.040, round to 3 decimal places. So you can see 0.227 plus minus 0.040. Then we need to continue to take 0.227 minus 0.04 to get 0.187, and we need to take 0.227 plus 0.04 to give us 0.267. So there we have it. We have the interval. Now there's a way to calculate this on the calculator, and you need to go to stats, test, and 1 prop z int, because we are using one proportion, and this is a normal distribution, so it's a z interval, right? And I will show you on the calculator how that looks in a second. So they will ask you for the x. In this case, the proportion, the number of people out of 300 that can roll their tongue is 68. The N sample size is 300. Confidence level is 90%, right? So if you put that in, that should give us the interval, confidence interval that we just found. I'll show you in a second. Okay, so to conclude, we need to say we are 90% confident that the interval from 0.187 to 0.267 captures, or another word for captures is contains, the true. Now, another word for true is population, right? True population proportion of adults who can roll their tongue. And so I need to now show you how to do it on the calculator. So, okay, to continue on the calculator, we go to stat, right? I don't know why it's, okay, go to stat, and then we go to test. We need to go 2 over test, and we need to scroll down to 1 when you see, because we're dealing with interval, right? We're estimating the true population proportion. When we're estimating it, we have to find the interval, because there's no way to find exactly the true population. We can only estimate where the true proportion or the population proportion will lie in, right? We need to give an interval. So we go to A, right? 1 prop Z int, and it will ask you, what's your X? X in this case is 68. And then out of 300 sample size, confidence interval is 90, right? You can put 0.9, it works the same. And then calculate, voila, right? You see the interval, right? The first line, 0.18691, comma, 0.26643. And there you have it. You have the sample proportion, 0.2266666, and you round to the nearest 3 decimal place, will be 0.227. Sample size is 300. Okay, so 8.2, section 8.2, concept 3 on choosing or determining the sample size. So students can determine the sample size required to obtain a confidence interval for a population proportion with a specified margin of error. So there are questions when you will be given the margin of error, right? You'll be given a margin of error with a confidence interval, and you're supposed to determine what the sample size is. So first thing is to understand where in the question did they say is referring to the margin of error. So here the margin of error is less than or equals to 0.02. How did I get the 0.02? It's actually right here. It says within 2%. Within 2% at a 95% confidence level. Now, in the previous question, we talked about what the formula is for margin of error. And I told you that the formula is Z star times square root of P hat times 1 minus P hat divided by N. Now, if this formula is less than or equals to 0.02, and we're supposed to find the N, and guess where N is? N is right in the denominator, and it's stuck in the square root sign. So you got to slowly make this through, right? Slowly work it out. Now, do we know Z star? No, we don't, right? Do we know P hat? Now, this is interesting because typically P hat, if they give it to you, you use the P hat, right? You use the sample proportion. But if P hat is not given, right, then you got to assume P hat equals to 0.5. Now, there's a reason why we assume P hat equals to 0.5. Then that is to maximize P hat times 1 minus P hat. Notice that P hat times 1 minus P hat is in the numerator, right? If you see, it's in the numerator in the formula. Okay, do you see the numerator underneath the square root sign, P hat times 1 minus P hat? So we want to maximize that. We want to maximize that numerator so as to maximize the sample size. So, all right, so we know now that P hat, let's use 0.5. Then Z star equals to inverse norm or inverse norm of 0.975. Now, that on your calculator is 1.960, which I we'll try to show you later on how do we get to inverse norm. And inverse norm is actually under second bars. Now, to explain why we put 0.975 instead of 0.95, the confidence level is 0.95. A lot of students always make this mistake. They see the confidence level, they put 0.95. In fact, it's better to draw the diagram. So here we draw 0.95, which is 95% confidence interval, right in the middle, right in the middle. And the tail end, that gives us 0.025. And we know that in inverse norm, we always add up area to the left, right? All the area to the left. So you add those two parts, 0.95 plus 0.025, it gives you 0.975. So we put in all the values. Z star is 1.960, and then P hat is 0.5. So we work that out. Now, from this stage, right, at this moment, it will be easier if we divide both sides by 1.960 to get rid of the 1.960 on the left-hand side, because it's multiplication, right? So we divide it. So you're left with square root of 0.5 times 0.5 over n, because 1 minus 0.5 is actually 0.5, right, in the numerator of the square root. So is less than 0.02 divided by 1.96. Then you square both sides, right? We square both sides so as to get rid of the square root sign, okay? So you have 0.25, because 0.5 times 0.5 is 0.25, right, in the numerator, divided by n, less than equals 2. Then you work out 0.02 divided by 1.96 in the calculator, and that gives you 0.0102. So how do we find n in this case? N could be solved if you just trade places with, if you just switch the n with the 0.0102 square, right? It's legal, right? You can actually switch it so that the 0.0102 square is in the denominator, and then the n goes over to the other side. Now, this is legal when both things are positive, right? If n is negative, then this doesn't work. By the way, n can be negative because, all the values should be a positive number, right? Sample size should be positive, not a negative. So if you work this out in the calculator, 0.25 divided by 0.0102 square, and that works out to be about 2,401. So now to conclude, right, if you were to work right out, we're supposed to interpret it, you say this: we would need at least 2,401, right? You always round up. There's no percent of adults, right? Because adults are always calculated as whole numbers. 2,401 adults to estimate the proportion who can roll their tongues within 2% at a 95% confidence interval.